Real-world applications of variable separable equations. Welcome, everyone. Up until now, in our previous lessons, we have been primarily focused on the algebraic mechanics, the step-by-step rules, and the technical process of solving differential equations. However, today we are moving beyond just the how and looking at the why. You see, the true power of differential equations doesn't just lie in the algebra, but in their incredible ability to model real-world phenomena. Think about the world around us. Many physical, biological, and even financial systems don't change randomly. Instead, they change at a rate that depends directly on the current state of that system. Now, there is a specific mathematical condition we look for. When these rates of change can be expressed as a product of two independent functions, we can use the method of variable separable equations to uncover the underlying governing law of that system. In this tutorial, we are going to apply this method to two very important areas. First, we will look at geometric modeling, where we use derivatives to describe the shape of curves. Then, we will move on to continuous growth models, which allow us to predict things like population growth or compound interest. Let's get started. 1. Geometric applications, the slope of the tangent. Now that we've established that we are moving from pure algebra into real-world applications, let's look at our first major application, geometric modeling. To understand this, we need to revisit a fundamental concept from coordinate geometry. Remember that the derivative, which we write as dy dx, represents the slope of the tangent line to a curve at any specific point, x, y. This is a crucial connection to make. If you encounter a word problem that describes how the slope of a curve behaves or changes at any given point, you aren't just looking at a geometry problem, you are actually being presented with a differential equation. Let's look at the conceptual framework for this. If a problem tells us that the slope of a curve at any point, x, y, is equal to some specific function of x and y, we can translate that directly into the mathematical notation. dy dx equals f of x, y. Now, as we learned in our previous lessons, if this function, f of x, y, is separable, we can use the method of variable separation to solve it. This allows us to find the equation for the entire family of curves that share this specific geometric property. To make this concrete, let's look at an example. Suppose we are asked to find the equation of a curve where the slope of the tangent at any point, x, y, is exactly equal to the ratio of the x-coordinate to the y-coordinate. In the next few slides, we are going to walk through the step-by-step process of translating this sentence into an equation and solving it. Step-by-step solution for geometric applications. First, we begin with step 1, which is translating that geometric description into a formal differential equation. Remember, in coordinate geometry, the slope of the tangent is mathematically represented by the notation dy over dx. The problem also mentions a ratio of the x-coordinate to the y-coordinate, which we write as x over y. By setting these two parts equal to each other, we arrive at our differential equation. Dy over dx equals x over y. Next, we move to step 2, where we perform the process of separating the variables. Our goal here is to get all the terms involving y on the left side and all the terms involving x on the right side. To do this, we multiply both sides by y and by dx. This leaves us with y dy equals x dx. Now, the variables are neatly separated and ready for the next stage. Finally, in step 3, we prepare to integrate both sides. We apply the integral symbol to both sides of our equation, so we have the integral of y dy equals the integral of x dx. We have successfully set up the calculus required to find the actual equation of the curve, which we will complete in the next slide. Now that we have identified our problem in the previous slide, where we are looking for a curve whose slope is equal to the ratio of the x-coordinate to the y-coordinate, let's walk through the mathematical solution step by step. Step-by-step solution for geometric applications, continued. Now that we have set up our integrals in the previous step, let's move on to step 4, where we actually perform the integration. when we integrate y with respect to y, we get y squared over 2. Similarly, integrating x with respect to x gives us x squared over 2. And of course, we must remember to add c, which represents our constant of integration. Next, let's move to step 5, where our goal is to simplify this equation so we can actually identify what kind of curve we are dealing with. To clean this up, let's multiply the entire equation by 2. This cancels out the denominators, leaving us with y squared equals x squared plus 2c now. To make it look even more standard, let's rearrange the terms by subtracting x squared from both sides. This gives us y squared minus x squared equals k, where we've simply renamed 2c as a new constant, k. Looking at this final form, we can recognize this as the general equation for a family of hyperbolas. So, by simply knowing how the slope behaves, we've successfully uncovered the geometric shape itself. 2. Continuous growth models. Now that we have seen how to use variable separation to find the equation of a geometric curve, let's shift our focus from shapes to something more dynamic: continuous growth models. You'll notice that many processes in the natural world, like the spread of a population, and in the financial world, like the growth of an investment, exhibit what we call continuous growth. The defining characteristic here is that the rate at which the quantity changes is directly proportional to the amount of the quantity present at that very moment. In other words, the more you have, the faster it grows. To turn this idea into math, let's look at our conceptual framework. Let's define P as the quantity we are tracking. This could be a population size or even a bank balance, and let T represent time. If this quantity grows at a constant rate, which we will call R, then the rate of change of P with respect to T, written as dP, dt, is proportional to P mathematically. We express this as dP, dt equals R times P. To see this in action, let's look at a classic example: continuous compound interest. Imagine a bank offers an account where interest is compounded continuously at an annual rate R. If we start with an initial principal, which we'll call P naught, our goal is to find a formula that tells us the total amount, P, after any number of years, T. In the next few slides, we are going to use the exact same separation of variables technique we used in our geometry example to derive this fundamental formula. Step-by-step solution for continuous growth models. Starting with step 1, we need to set up our differential equation. Remember, the core idea of continuous growth is that the rate of change is proportional to the amount present. In our specific case, the rate of change of the principal, which we've called P with respect to time, T, is equal to the interest rate, R, multiplied by the current principal, P. Mathematically, we write this as dP, dt equals Rp. Once we have our equation, we move to step 2, which is the process of separating the variables. Our goal here is to get everything related to P on one side and everything related to T on the other. To do this, we divide both sides of the equation by P, and then multiply both sides by dt. This leaves us with one P term on the left and our time terms on the right, resulting in 1 over P dP equals R dt. This setup is crucial because it prepares us for the integration step that we will see in the next slide. Now that we have established the conceptual framework for continuous growth in the previous slide, let's move into the actual mechanics of solving the interest problem. Step-by-step solution for continuous growth models, continued. Now that we have successfully separated our variables in the previous step, placing all the P terms on the left and the time terms on the right, we move on to step 3, which is to integrate both sides of the equation. We are looking at the integral of 1 over P with respect to dP, which is set equal to the integral of our constant rate, R, with respect to dt. Moving into step 4, we perform the integration to solve these integrals. On the left side, the integral of 1 over P gives us the natural logarithm of the absolute value of P on the right side. Integrating the constant R with respect to T simply gives us R times T. And, as always with indefinite integration, we must include our constant of integration. See, this leaves us with the equation. Natural log of the absolute value of P equals RT plus C. We will use this result in the next slide to isolate p and find our final growth formula. Step-by-step solution for continuous growth models, continued. In step 5, we solve for p by exponentiating both sides of the equation. This means we apply the base e to both sides. On the left, e raised to the power of the natural log of the absolute value of p simplifies directly to the absolute value of p on the right. We have e raised to the power of rt plus c using our laws of exponents. We can split this into e raised to the power of rt multiplied by e raised to the power of c now. Here is a helpful trick. Since e raised to the power of c is just another constant, we can rename it as a capital A. This gives us our general solution. P of t equals a times e raised to the rt. However, we aren't finished yet. We need a specific formula for our specific bank account, which brings us to step 6. We must apply the initial condition to find the value of this constant, a. We know that at time t equals 0, the initial principal is p naught. If we plug 0 into our equation, we get p naught equals a times e raised to the power of r times 0. Since e raised to the power of 0 is just 1, we find that p naught equals a times 1, which simply means it equals p naught. Finally, in step 7, we can write our final particular solution. By substituting p naught back into our equation, we get p of t equals p naught times e raised to the rt. As you can see, this is the standard, famous formula used for continuous compounding in finance. It's a beautiful result that shows exactly how money grows over time. Now, before we wrap up, let's look at some common pitfalls to avoid when solving these types of problems. Now that we have integrated both sides in the previous step and arrived at the natural log of the absolute value of p equals rt plus c, we need to isolate our variable p. Common mistakes to avoid. First, let's talk about incorrect separation. This is perhaps the most frequent error I see. When you are looking at a differential equation, you must remember that the method of variable separation only works when the variables are linked by multiplication or division. A common mistake is trying to separate terms that are being added or subtracted. For example, if you have the equation di by dx equals x plus y, you might be tempted to move the y to the left side to get di by dx minus y equals x, and then try to integrate. However, you cannot integrate the y terms separately from the x term in that setup. Variable separation only works when you have something like di by dx equals x times y, where the variables are products or quotients. Second, be very careful about neglecting the constant c, as we saw in our continuous growth models. That constant of integration is not just a formality. It is mathematically essential. If you forget to include c after integrating, you will find it impossible to incorporate your initial conditions, such as the initial principal, p0. Without that constant, you won't be able to bridge the gap between the rate of change and the actual starting value, which ultimately leads to an incorrect final formula. Finally, watch out for logarithmic errors. When we were solving the growth model, we encountered the integral of 1 over p dp, which results in the natural log of the absolute value of p. A common stumbling block occurs when students reach the step where they have the natural log of p equals rt plus c, and they forget how to isolate p. Remember, to undo a logarithm, you must use its inverse function, which is the exponential function, e raised to the power of the expression. If you forget to exponentiate both sides, you'll never arrive at that crucial exponential growth formula we derived earlier. Now, before we wrap up today's session with our final summary, I want to pause and discuss some common pitfalls. Even if you understand the steps we've covered in the geometric and growth models, it is very easy to make certain errors that can derail your entire solution. Let's look at 3 specific mistakes to watch out, easily avoided. Keep these 3 points in mind as you practice, and you'll avoid the most common traps in differential equations. Key takeaways. First, let's revisit the geometric interpretation. Throughout our first example, we saw that the derivative, which we write as dy over dx, isn't just an abstract symbol. It is our primary mathematical tool for representing the slope of a tangent line. When you encounter a problem describing how a curve's steepness changes at any given point, You are looking at a geometric differential equation. Next, let's look at the growth law. In our second application regarding continuous compound interest, we observed a fundamental pattern. Any system where the rate of change is directly proportional to the current value, which we can express as dy over dx equals k times y, will always result in an exponential solution of the form y equals c e to the power of k times x. Whether it is population growth or bank balances, this exponential pattern is a universal consequence of that specific proportional relationship. Finally, I want you to remember the general process flow. Whenever you face a complex word problem, don't feel overwhelmed. Just follow this logical workflow. Start by translating the word problem into a differential equation, then use the method of separation to isolate your variables, proceed to integrate both sides, and finally, solve for your specific constant to find your particular solution. All right, we have reached the end of our tutorial. Let's take a moment to recap the most important points we've covered today so you can consolidate your learning. If you can master this sequence, you can solve almost any application involving variable separable equations. Great job today!